Chapter 6, Musical Hearing. Hearing is considered by some to be the most important sense in humans. Whether it is or not, a thorough understanding of the physiology of the hearing mechanism is essential to understanding many aspects of musical behavior, because it is primarily the sense of hearing that makes music possible. 3 elements are needed for the perception of sound to take place: a source of vibrations, a medium of transmission, and a perceiver. The first 2 elements were discussed in the previous chapter. This chapter includes a discussion of the third element, the perception of sound. In the following pages, a sound wave will be traced from outside the ear to the brain, and the perception of psychological attributes of sound will be discussed. Throughout this discussion, the reader is urged to keep in mind the incredible sensitivity of the hearing mechanism and its extreme miniaturization. For instance, one can perceive sound when the eardrum has been deformed as little as 1/10 of the diameter of a hydrogen molecule. The softest sounds we can hear result from air pressure changes of 2/10 of atmospheric pressure, and the ratio of the loudest sound we can hear to the softest is more than 1,000,000,000,000 to 1. Kuncher, 2008, found that listeners could discern temporal alterations on a time scale of 5 microseconds. One of the bones of the middle ear, the stirrup, is the smallest in the human body, at about half the size of a grain of rice, and Reisner's membrane in the cochlea is only 2 cells thick. This marvelous engineering should give musicians and all others who enjoy the sounds they hear a feeling of awe and appreciation. The hearing mechanism. Outer ear. The outer ear consists of the visible ear on the outside of the head, the auricle or pinna, ear canal, and eardrum. The hearing process begins as sound pressure waves traveling through the atmosphere strike the ears. Ears, as one can readily observe, vary considerably in size and shape from person to person. Some animals have muscular control over their ears and can tilt or rotate them in different directions and aid to the localization of sound. Humans do not possess this ability and instead turn their heads toward a sound to aid in localization. A commonly supposed function of the outer ear, pinna, is that it catches sound waves. The sound waves coming towards us from all sides, however, have wavelengths measured in many inches, feet, or even yards, whereas the diameter of the pinna, and especially of the inner conch, the ear canal, is not much more than 1 inch. The sound is therefore scattered rather than collected and focused. Man's outer ears do help to make sounds originating from in front of the head slightly more intense than those originating from behind, and this aids in sound localization. Cupping a hand behind an ear demonstrates how the outer ear makes sounds louder and easier to hear. Another aid to sound localization is the inner contour of the ear shell. As sound waves reflect off the ridges and folds of the outer ear, they provide localization cues to the brain. Using a dummy head equipped with artificial ears, researchers demonstrated that by gradually smoothing out the inner surface of the outer ears, they were able to reduce the ability to localize sounds. Localization of sounds is also greatly aided by timing cues. Sounds arrive at the 2 ears a microsecond apart. E.g., a sound coming from your left side must go around the head to reach the right ear, and the brain uses these discrepancies in arrival time to locate the direction of the sound. Another portion of the outer ear is the ear canal, external auditory meatus. This air-filled cavity has 2 protective devices to keep unwanted dust particles or other foreign bodies from entering the ear. The outermost edge is lined with hairs, and the surface of the ear canal is lubricated with a sticky wax. The primary function of the ear canal is to channel air pressure waves to the eardrum. It also acts as a resonator and amplifies sounds in the range of 2,000 to 4,000 hertz, as much as 15 decibels, precisely the frequencies most important for music and speech. Finally, the ear canal has the function of controlling the temperature and humidity of the eardrum, which lies at the far end of the canal. The eardrum receives air pressure waves from the atmosphere via the ear canal and vibrates in accordance with the frequency and intensity of the waves. It is an extremely sensitive membrane. Responding to the movement of molecules of air, the eardrum transmits a wide variety of vibrations, from the faintest whisper to the loudest explosion. Evidence of the eardrum's sensitivity is the fact that its thinnest portion is only 0.055 millimeters thick. Middle ear. Between the eardrum and the cochlea in the inner ear is the air-filled cavity called the middle ear. This cavity is not completely closed, but has an opening into the oral cavity, the eustachian tube. The eardrum connects with the inner ear by means of 3 small bones, known collectively as the ocelus, and separately as the hammer, or malleus, the anvil, or incus, and stirrup, or stapes. These bones are among the smallest in the human body. The ocelus serve as a link between the outer ear and inner ear. At one end, the hammer is attached to the eardrum, and at the other end, the stirrup is connected to the cochlea at the oval window. See figure 6.2. I'm going to attach that right here, so if you want to pause and look at that, you can. A sound wave traveling in the atmosphere reaches the ear and is channeled through the ear canal to the eardrum. The eardrum, in sympathetic vibration with the sound wave, vibrates back and forth, moving the hammer, anvil, and stirrup. These bones not only transfer the vibration to the oval window, but due to their specific motions and the disparity in size between the eardrum and the oval window, also amplify the vibrations. As they travel through the air, sound waves meet with very little resistance, especially when compared to the resistance found in the dense fluid of the cochlea. In fact, the impedance of cochlear fluid is approximately 3,750 times greater than that of air. If a sound wave traveling through the air struck the oval window directly without receiving amplification from the auditory canal, the eardrum and the ocelus, less than 1% of the energy would be translated to the fluid-filled cochlea. Actually, the motions of the middle ear are quite complex, but the important fact is this increase in energy from the eardrum to the oval window. The increase in energy from that found at the eardrum to that necessary at the oval window as it pushes against the perilymph is created in 3 ways. First, the eardrum is much larger than the oval window, which causes an increase in pressure of 35 times. Second, the eardrum buckles in the middle, which doubles the pressure at the oval window. Third, ossicles, acting as levers, increase the pressure by a factor of 1.15. Taking these 3 factors into account gives an overall increase of pressure at the oval window of 80.5 times. The math breaks down to 35 times 2 times 1.15 equals 80.5. 3 muscle actions combining to form the acoustic reflex play an important role in protecting the ear against loud noises. First, the muscles that control the eardrum can contract and draw the drum into a conical shape. This stiffens the membrane so that it cannot vibrate so much. Second, the muscles of the ossicles can twist the bones so that they are somewhat rotated and lose a little of their amplifying efficiency. Third, an attached muscle can alter the stirrup in relation to the oval window, again causing a loss of amplification. Also, the eustachian tube, normally closed, can be opened by opening the mouth or swallowing. This allows air pressure to be equalized on both sides of the eardrum. Unfortunately, even with all these protective devices, the ear has no way of protecting itself against sudden loud noises. Each of the muscle actions can take place only after a realization that a sound is too loud, and even though the reaction is very quick, about 10 to 20 milliseconds, It is not quick enough to protect against a sudden, unexpected, loud noise. Inner ear. The oval window separates the air-filled middle ear cavity from the fluid-filled inner ear. The inner ear consists of the semicircular canals and the cochlea. The semicircular canals serve an important function in determining body position, but they are not involved in the process of hearing. The cochlea has another surface membrane besides the oval window. This is the round window, which serves to release pressure built up in the cochlea. See figure 6.3, and I will insert that right here so you can pause and look at it if you want. The cochlea is a spiral-shaped body of 2 1/2 turns, no bigger than the tip of a little finger. It is about 1 1/3 inches long and perhaps 1/8 inch wide at its broadest point. Along most of its length, it is divided by the cochlear duct into two parts, the vestibular canal and the tympanic canal. These two canals are connected at the tip of the cochlear spiral by the helictotrema and are filled with perilymph. The cochlear duct is filled with endolymph and is bound on one side by Reisner's membrane and on the other side by the basilar membrane. The system of vestibular and tympanic canals with the cochlear duct is so tiny that it only takes a fraction of a drop of perilymph, a liquid almost identical with spinal fluid, to fill the canals, and even less endolymph, similar to the fluid within cells, to fill the duct. All right, I'm also going to be inserting figure 6.4. Figure 6.4. The cochlea and auditory hair cells. On the left is a cast of the cochlea, which is a hollowed canal in the temporal bone. On the right are auditory hair cells, with one row of inner hair cells at the top and 3 rows of outer hair cells at the bottom in their characteristic V or W shape. Reisner's membrane, only 2 cells thick, is the thinnest in the human body. The basilar membrane is made of relatively stiff fibers, and from the oval window to the apex widens to 6 times its original size. One side of the basilar membrane is attached to a bony shelf. The other side is attached to ligaments and is free to vibrate. Resting on the basilar membrane is the organ of Corti. The organ of Corti contains the arches of Corti, which support 1 inner and 3 outer rows of sensory hair cells. There are about 3,500 inner hair cells and 20,000 outer hair cells. Approximately 30,000 auditory neurons synapse onto the inner hair cells. Outer hair cells can shorten their length up to 2 microns, as many as 30,000 times per second. This is 100 times faster than anything else in biology. The conjecture is that this rapid length change may enhance the auditory signal, improving sensitivity and fine-tuning. Overlapping the organ of Corti is the tectorial membrane. About 100 microscopic thread-like filaments called stereocilia emerge from each outer hair cell and are embedded in the tectorial membrane. About 50 stereocilia emerge from each inner hair cell, but these are not embedded in the tectorial membrane. Quote, at the threshold of hearing, the faintest sound we can hear, tiny filaments associated with the stereocilia move about 0.04 nm, about the radius of a hydrogen atom. I'm actually not sure what the abbreviation of NM is. I'm going to go look it up right now. Stands for nanometer. So going back to the quote, at the threshold of hearing, the faintest sound we can hear, tiny filaments associated with the stereocilia move at about 0.04 nanometers, about the radius of a hydrogen atom. Autoacoustic emissions, or OAEs, are sounds emitted by the cochlea that are recorded as acoustic vibrations in the ear canal. These sounds are created by a reverse electrical to mechanical transduction process in the outer hair cells. Their presence may explain the role of outer hair cells in sharpening pitch perception. Measuring OAEs provides a non-invasive means of studying the mechanics of the cochlea and forms an important part of clinical hearing tests. OAEs can be suppressed through activation of the efferent system, i.e., from brain to ear. There is a relationship between the suppression of OAE and pitch matching and pitch discrimination in trained musicians, as trained musicians have better OAE suppression than musically untrained individuals. Untrained individuals did not show a relationship between OAE suppression and pitch skills. Therefore, musical training appears to have a positive effect on OAE suppression. Linking the inner ear to the brain is the auditory nerve, which allows for two-way communication. For each cochlea, there are about 50,000 fibers that carry information from the cochlea to the brain along ascending pathways and 1,800 fibers that carry signals from the brain to the cochlea along descending efferent pathways. About 93% of the fibers of the auditory nerve supply the inner hair cells, which represent only 20% of the total number of hair cells. While many outer hair cells may converge on a single auditory nerve, each inner hair cell may stimulate up to 20 auditory nerve fibers, most of which are afferent, which is going to the brain. Because of this arrangement, inner hair cells provide more acoustic information. Efferent nerves, or information coming from the brain to the cochlea. Efferent nerves bringing information from the brain to the inner ear may have to do with increasing the frequency resolution of the inner hair cells. As the stirrup pushes on the oval window, causing it to move in and out, waves are propagated through the perilymph and passed along the vestibular canal to the helicotrema, making a return trip through the tympanic canal. At the end of this two-way trip through the spirals of the cochlea, the waves push against the round window. When the oval window is pushed in by the action of the stirrup, the round window is pushed out by the pressure of the waves traveling through the perilymph. The energy transmitted by the movements of the round window is released into the air cavity of the middle ear, where it returns to the atmosphere via the eustachian tube. On its journey through the vestibular and tympanic canals, the pressure wave transmits some of its energy to the membranes of the cochlear duct and the endolymph contained in it. As the membranes and the endolymph vibrate, the arches of Corti are also vibrated. Quote, when the basilar membrane is deformed in vibration, the rectular lamina, tectorial membrane, and organ of Corti slide with respect to each other, bending the hairs. End quote. It is this shearing action caused by the membranes traveling in opposite directions that excites the hair cells. Hair cells can be stimulated when they are deformed as little as 100 picometers, or 1/1,000,000th of a meter. This An analogous experience can be felt if the hairs on the arm are lightly stimulated. As the hairs are bent, they propagate signals to the brain transmitting information about the touch sensation, such as whether the touch was closer to the wrist or the elbow. The hair cells act as transducers, and it is at this point that the mechanical energy of the waves in the cochlear fluid is converted to electrochemical energy. The hair cells are arranged along the length of the basilar membrane in such a way that those nearest to the oval window respond to higher frequencies, and those nearest the helicotrema at the far end respond to lower frequencies. It is interesting to note that the musically most important range of frequency, approximately 20 to 44,000 hertz, covers roughly 2/3 of the extension of the basilar membrane, 20 to 35 millimeters from the base. All right, page 109. From ear to brain. Auditory information does not travel from the inner ear to the primary auditory cortex along a simple straight line route. Rather, information is transmitted along a very diffuse and intricate pathway. Since even the brief overview that follows is fairly complicated, it may be important to remember these general points. 1. Analysis of auditory information takes place in many localized processing centers scattered along a diffuse pathway between the inner ear and the auditory cortex. 2. Each of these processing centers analyzes the auditory information for a particular feature, such as location of the source of the sound. And 3. All these bits and pieces of information are put back together to create a coherent sound experience with meaning, parentheses, music, in the primary auditory cortex and the surrounding association areas. Frequency representation of the basilar membrane is retained along the auditory nerve. Fibers in the center of the auditory nerve carry information about low frequencies, and fibers on the outside carry higher frequencies. Maintenance of frequency information in a spatial representation or map is called tonotopicity or tonotopical organization. The first portion of the auditory nerve is sometimes referred to as the bottleneck of auditory sensation because at this point, all the information relayed between the ear and the brain is carried in a single bundle of fibers, unlike the more diffuse pathways higher in the brain. The auditory nerve, as part of the 8th cranial nerve, divides as it enters the brainstem and sends fibers to both the upper dorsal and lower ventral cochlear nuclei. See figure 6.5. More fibers go to the larger ventral cochlear nucleus than to the smaller dorsal cochlear nucleus. Beginning at this level, the auditory pathway rapidly increases in diversity and complexity. Tonotopic organization is retained, with higher frequencies represented in the dorsal cochlear nucleus and lower frequencies in the ventral cochlear nucleus. Different neurons in the cochlear nuclei respond to different aspects of the acoustic information, such as stimulus onset or offset. The cochlear nuclei not only relay information, but also sort, enhance, and encode information to be sent to higher auditory nuclei. As fibers leave the cochlear nuclei, the first crossovers in the auditory pathway occur, and some fibers are sent to the superior olivary complex and inferior colliculus on the opposite contralateral side. This is the beginning of bilateral representation of sound. Other fibers that leave the cochlear nuclei extend to the superior olivary complex and inferior colliculus on the same side, and to the reticular formation. The superior olivary complex is tonotopically organized in some portions. The portions not so organized are believed to be involved in processing by binaural time and intensity disparity cues for sound localization. Also, at the superior olivary complex, there are already individual cells that receive incoming signals from both ears as well as from the eyes. Some of the fibers from the ventral cochlear nucleus extend to the reticular formation. The reticular formation communicates with virtually all areas of the brain, including the cortex and spinal cord. There is a parallel pathway in the reticular formation, not shown in figure 6.5, that connects with descending tacts in the spinal cord to allow for reflex types responses to sound stimuli. The descending or efferent pathway emanating from the reticular formation also serves to inhibit lower auditory centers and elevate thresholds of hearing. The ascending pathway from the reticular formation serves to alert the cortex of important upcoming signals. Animals whose classical auditory pathways have been cut regain their ability to respond to sounds using this alternate auditory pathway through the reticular formation. Cells in the medial olivary complex respond to temporal delays and are tuned to specific tonal frequencies. Because there are more cells tuned to lower frequencies, these nuclei may have a significant role in locating the source of lower frequencies. Cells in the lateral superior olive specialize in detecting intensity differences in the two ears and provide localization of higher frequency tones. As sound waves travel through the air, the head casts a shadow, such that there is a slight time differential in the arrival of the sound wave at the two ears. Since lower frequencies have longer waves, this shadow effect has more consequences for higher frequency tones. One role of the olivary complex, then, is to create a spatial map. The last point for fibers from one ear to cross over to the opposite side is at the inferior colliculus, which receives its fibers from the superior olivary complex via the lateral lemniscus from the cochlear nuclei. These crossing fibers, which extend to the contralateral inferior colliculus, are probably responsible for certain forms of sound integration, since up to 80% of the cells can be stimulated binaurally. There is a considerable tonotopical organization with low frequencies at the sides and higher frequencies in the center. The final relay station before the auditory pathway reaches the cortex is the medial geniculate body, located in the thalamus. Frequency-specific fibers leaving the medial geniculate body fan out in ascending auditory radiations and provide frequency information to the auditory cortex. For a detailed examination of all the auditory way stations between the inner ear and the auditory cortex, see Altschuler, Bobin, Clopton, and Hoffman, 1991. The ratio of contralateral to ipsilateral fibers is approximately 5:1. As a result, conduction is faster and stronger for the crossed pathway. Thus, while both ears send all information to both sides, each hemisphere listens more carefully to the ear on the opposite side and will suppress information from the ipsilateral side if there is any conflict. The auditory cortex. The final connection for the auditory pathway is in the temporal region of the cerebral cortex. The primary auditory projection areas lie in the superior temporal gyrus and occupy a surface only 1/2 to 1/3 the size of the optic cortex. This represents 0.3 to 1% of the surface of the entire cerebral cortex. According to Weinberger, 1999, quote, the primary auditory cortex lies in Heschel's gyrus, which is within the sylvian fissure. The surface of the primary auditory cortex thus extends more or less perpendicular to the surface of the temporal bone, in depth within the fissure. End quote. That is, the auditory cortex is not only on the outer surface of the cortex, but also folds inward into the recesses of the brain. There are about 100 million auditory cells in each auditory cortex, and various neural units within the auditory cortex respond to different types of sound stimuli. For instance, some neurons respond to pure tones and others to complex tones. I'll be inserting figure 6.6 on the screen. You want to look at that? Page 112. Other neural units respond to stimulus onset, termination of a stimulus, or to on-off. The primary auditory cortex is further organized in that tonotopicity is retained, and for pure tones, cells are systematically arranged according to their characteristic frequencies. Parentheses, that is, the frequencies to which they best respond, end parentheses. Some cells respond not only to pure tones, but to complex tones as well. Also, cells are arranged so that those excited by one ear are separated from those inhibited by the other ear. In other words, ear dominance is anatomically represented. As shown in figure 6.6, the secondary auditory cortex is adjacent to the primary auditory cortex, where additional sound processing takes place in the planum temporal, planum polar, belt, and parabelt areas. Contralateral processing, i.e. listening preferentially to sounds coming from the opposite ear, and tonotopical organization, i.e. retaining a frequency map, are stronger in primary than secondary areas. Responses to sound occur in primary sooner than secondary, and primary areas only respond to the perception of sound, whereas the secondary areas can also respond during sound imagery. Differences in primary and secondary auditory cortex may represent the transition from processing physical characteristics of sound to processing information about the sound object in context. In the womb, the auditory cortex develops sufficiently such that the fetus can respond to sounds during the last 3 months of pregnancy. Assuming a lack of conscious awareness, prenatal listening experiences can hardly be called musical. Nevertheless, there are indications that the fetus can register and remember musical sounds that will affect behavior after birth. However, since the brain does not know what particular sounds the baby must attend to, i.e. what languages, music, or environmental sounds, the infant brain has up to 150% more synaptic connections in the auditory cortex than it will have as an adult. Learning experiences throughout childhood will shape the brain into its eventual configuration through neural pruning. Neural pathways supporting sounds heard repeatedly or that have particular meaning, such as the sound of a mother's voice, are strengthened. Synaptic connections activated by random or meaningless sounds wither and may disappear altogether if they are never heard again. Once we learn the sounds of our culture, it is more difficult to perceive other acoustic patterns. In most situations, the baby is surrounded by music of the culture through television, the radio, family members singing, and so on. And thus, for most American babies, neural pathways supporting Western tonal music are developed. Insufficient exposure to sounds causes deficits in neural development, and cortical projections to and from the auditory cortex are diminished. Thus, although congenitally deaf adults have similar auditory areas as hearing adults, they have fewer pathways leading in and out. The auditory cortex, like the rest of the cerebral cortex, is commonly divided into 6 layers. Until about 4 months, functional neurons in the auditory cortex are restricted to layer 1, the top outer portion of gray matter. Thus, the infant's ability to process auditory information is mostly limited to brainstem analysis. Between 6 months and 5 years, projections reach the deeper layers, 4 through 6, and auditory processing moves from brainstem to auditory cortex. This process results in increasing linguistic and musical perceptual skills. Over the next 5 or 6 years, mature axons in layers 2 and 3 appear, and the auditory cortex is more strongly connected throughout all 6 layers, between hemispheres, and to the surrounding auditory association areas. These association areas provide an interpretive function. They place information gleaned from brainstem and primary auditory cortex into a broader context. Eventually, this information is sent on to convergence zones that combine auditory information with input from the other senses. Pausing on page 113. Progressive development of the auditory cortex is demonstrated in infant studies. At the age of 2 weeks, the detection threshold for changes in pure tone frequencies is 50 decibels poorer than adults. This gap narrows to 15 to 30 decibels at 3 months and 10 to 15 decibels from 6 to 12 months. Similar developmental progression is seen for intensity discrimination. Another critical aspect of auditory perception is auditory stream segregation that allows the baby to parse sounds from mother's voice and the television into separate sources. Amazingly, 2 to 5 day old newborns are as adept at this task as 18 to 23-year-olds. In addition, 2-month-old babies can discriminate between target and alternated sound patterns, but 31% at 3 months, 58% at 4 months, and nearly all at 6 months perform with more adult-like responses. It appears that there are inherent auditory mechanisms for the perception of both language and music, and that a developmental trajectory in the auditory cortex can be demonstrated for the perceptual aspects of both. Brain images of 1 to 3 day old newborns in response to normal and altered versions of Western tonal music indicated that neural networks for music processing are present at birth. Infants respond to music at very early ages. They prefer consonants over dissonance, and they can detect melodic changes in terms of pitch, rhythm, tempo, and contour. Zenter and Irola, 2010, demonstrated that 5 to 24-month-old infants engage in more rhythmic activity to music than to speech. They exhibit some degree of tempo flexibility, and the extent to which they entrain with musical rhythms is related to positive effect. Infant pre-verbal and pre-musical vocalizations also demonstrate modulation of timbre, melodic contour, rhythm, and so on at very early ages. The fact that these behaviors appear so early is an indication that these skills are more due to inherited neural wiring than to learning. Another aspect of auditory cortex development is hemispheric asymmetry. That is, differences between the left and right sides. In 2/3 of hearing adults and in congenitally deaf adults, the auditory association area is larger on the left than on the right. Although asymmetrics may be affected by learning, they are already present at birth. At 29 weeks gestation, the left side is already larger than the right. The right hemisphere is more specialized for spectral processing, and the left for temporal resolution, though again, this may be more true of primary than secondary auditory cortex. For example, speech sounds are often lateralized to the left and music to the right hemisphere. However, such lateralization is often affected by sex, age, and training. As indicated previously, over 80% of the fibers cross over from the inner ear on one side to the auditory cortex on the other side. Left ear/right hemisphere preferences for music timbre discrimination were demonstrated in 4-day-old newborns and also in 2, 3, and 4-month-old infants. More sophisticated processing in 8.5-month-old babies indicated left ear/right hemisphere preferences for melodic contour changes and right ear/left hemisphere preferences for preservation of melodic contours. Hemispheric preferences persist as 5 to 7-year-olds showed an increase in left auditory cortex activations for rhythmic processing and right auditory cortex activations for melodic processing. These left-right differences are smaller than those found in adults, indicating a continuation of this developmental arc. As early as 2 days after birth, neonates can detect the sound of their mother's voices. Limited musical timbre judgments can be made at the end of the first week. By 8 months, infants can discriminate timbre changes important in both speech and music. In terms of timing, electrical activity responses to durational changes in the brain of 2 to 6-day-old newborns are similar to those in older children and adults. Electrical activity in the brains of 3, 6, 9, and 12 months old showed an overall increase in power while listening to music. By 7 months, infants can remember music they previously heard. The receptive fields of certain individual auditory cortex neurons are capable of being retuned to respond more favorably to a different frequency. Retuning neurons indicates that learning can cause modifications in sensory processing. Another idea is that place information, tonotopic organization, in the auditory cortex is based on frequency for pure tones and pitch for complex tones. This indicates that considerable frequency analysis has taken place at the subcortical way stations. For more on pitch perception, see Chapter 7. Using a superconducting quantum interference device, parentheses, SQUID, researchers documented that there is a common mapping in the primary auditory cortex, with the pitch for complex tone superimposed onto the same areas as frequency for pure tones. Thus, one group of cells responds to middle C, another to C sharp, and so on. Quotes, this kind of tone map shows that each octave, parentheses, factor of 2 in frequency, of the frequency scale spans equal distance across the cortex, much like the arrangement of the keys on a piano keyboard, end quote. Higher tones are mapped deeper in the fold, and lower tones are nearer to the surface. There are a number of auditory cortical maps, and these are plastic, responding to learning experiences. One research group identified 5 areas in the human auditory cortex that contain at least 6 tonotopic organizations that systematically increase in frequency sensitivity, and additional areas that are not tonotopically organized. In relation to music processing, the auditory cortex responds differentially depending on the musical elements involved and the musical context. Although different cells in the auditory cortex respond best to specific frequencies, their response sensitivity can be altered by experience or training. For example, melodic patterns make a difference to individual cells, as they respond differently to a tone depending on placement in the melody, whether the melody is ascending, descending, or has a more complex contour. Training can significantly improve auditory perception. For example, compared to untrained controls in auditory perception tasks, trained musicians were much more accurate, requiring a difference of only 0.67% of a bass tone compared to 2.95% to distinguish between two pitches, and much faster, 33.7 milliseconds compared to 76.7 milliseconds. Melody, harmony, rhythm, and timbre can be processed preferentially in either the left or right auditory cortex, depending on levels of training and other variables. For more information, see Chapter 9. There may be significant anatomical variations in different portions of the auditory cortex between hemispheres. For instance, some areas, parentheses, Heschel's gyrus and the planum temporal, are frequently larger in the left hemisphere, while another portion, parenthesis, the frontal area of the superior temporal region, is usually larger in the right hemisphere. Wide variability also exists between subjects, some of whom have a larger middle, basal, or superior temporal subregion. Quote, evidently, this type of variability is associated with individual differences in the development of certain auditory functions, parentheses, for example, those connected with music. The primary auditory zone is surrounded by association areas. These areas serve interpretive functions. Damage to these or other portions may cause amusia, the loss of musical skills. For instance, damage to one area produces an inability to understand or interpret sounds, while primary sensory discriminations are not impaired. Other areas are concerned with frequency or temporal aspects, with the association of sound in past experiences, or with the retention of oral memories. The roles of the subcortical areas, the primary auditory cortex, and the association areas are not completely understood. Research with animals indicates, for instance, that the auditory cortex may not be necessary for certain aspects of hearing, and that many auditory discriminations may be mediated at subcortical levels. In general, however, it appears that the subcortical levels provide basic auditory discriminations. The auditory cortex makes more sophisticated discriminations, and the association areas provide integration, interpretation, and understanding. Also, a sound stimulus perceived in one ear is better processed by the hemisphere on the opposite side. Finally, There are anatomical variations in various areas of the auditory cortex and surrounding association areas that may account for some of the variations in the abilities shown by individuals. Conclusion. Of all our senses, hearing is the most pervasive. Although the other senses can be regulated somewhat, we can never escape from sound. With our eyes closed, we cannot see. With our nose held shut, we cannot smell. As long as we do not touch anything with our skin or tongue, there is no sensation of touch or taste. However, no amount of putting our hands over our ears will ever shut out the world of sound. Even during sleep, the body responds to sounds that are not consciously perceived. Hearing has other advantages in that we can detect information emanating from considerable distances. We can hear sound even when the source of it is not visible. Sound travels through a forest, across a valley, and from within hiding places. In addition, we can understand emotional content encoded in sound. At the outset, much was made of the delicate engineering of the hearing mechanism. Unfortunately, we live in much louder environments than the ears were designed for. Thus, we are at considerable risk of noise-induced hearing loss. This topic and the implications it has for musicians are explored in Chapter 15, Music and Health. Our sense of hearing has had an important consequences for human beings and the music we produce. We may have invented music in part because we were surrounded by a sound world from which we could not escape. Musical sound results, at least in part, from the human need to organize and elaborate sensory input. Knowledge about the way the hearing mechanism works influences our understanding of general musical behavior. Beyond simply knowing about the hearing process, understanding musical behavior requires comprehension of the relationships among the physical frequencies, amplitude, signal, shape, and time, and the perceptual, pitch, loudness, timbre, and duration. All right, that is the end of Chapter 6. I will post the discussion questions. Thanks for listening.